Sairam and welcome to this session where we are going to look at how to solve linear equations. Let us begin this session with a prayer. Om Sai Ishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. So let's just try to remember what we did in the previous session. The essence of the previous session was what we called as the column picture, and we also looked at the row picture. Okay, the row picture represents the equations as such. So we look at individual linear equations and try to draw, let's say in R2 we draw a line, then that forms the row picture, whereas column picture is talking about the column vectors. Right? So we pick up the coefficients of different terms or different variables in each of the equations, and those coefficients form column vectors, right? And that is the picture we are looking at and we are calling it as the column picture. So in this session, right, what we looked at as column picture and row picture is going to come of use. So first let's try and attempt solving linear equations, and the technique that we are going to look at today is called elimination. Now elimination is a technique that we would have learned quite early in our school days as well. So let me just try and take an example. Let's say that we have x minus y equal to 3 and say x plus y equal to 3. If we are asked to solve this, it's a typical way. What we do is we add the two equations and we may say 2x, y's and y's get cancelled, and 2x equal to 6 and therefore x is equal to 3. We substitute this in any one of the equations and we get therefore y is equal to 0, right? But in case we are given, let's say minus x plus y equal to 3 and say x plus y equal to 3, right? We may tend to say, let me continue to add, because this time x and x will get cancelled. I may get 2y equal to 6, therefore y is equal to 3, which means that x is equal to 0, right? So now we see something interesting. In this case, we were able to identify that adding the equation would cancel the y's, and therefore I can calculate the x and then use this value to find the y. But when we move here, the same technique, right? Yeah, adding the equation look the same, but the change is that we add the equations, but then we get the y value now, right? Now remember that as a human, right, we have that intelligence to actually look at two equations and we know whether we need to add or subtract. We have to multiply an equation and then add, etc., and we know what is the variable that's going to come out, and therefore we have to substitute the other variable, right? As a human, we understand that through our own intelligence, right? But then the approach that we are going to take here is we want to look at an algorithmic approach to elimination, right? So we don't want something where we can do it in the human way. So when I say algorithmic way, we are saying we must have a standard technique, right? So moment we have two equations, maybe we should try and look at eliminating the x and maybe keeping the y, calculate the y and then do a substitution and find the x, right? That's one technique. So when I have three variables, similarly first I will eliminate x, then maybe we'll eliminate y and then find z, substitute it back, and then I can find y and then x, right? So that is the idea we're looking at. It's not going to be our elimination idea as we studied in the school days, but the approach here is to make it more algorithmic. Okay, so let's proceed trying to get into this method. Okay, let's say that we have these two equations with us in two variables, and what's the algorithmic approach in order to do elimination? In elimination, what we are going to do is we are trying to eliminate the first variable, and we have to eliminate this first variable from the second equation, so that we can replace this equation. While removing this, we will only be left with the y term. We can calculate that and then get back and substitute to find the x value, right? Now in order to eliminate the x here, we may have to do something by subtracting this equation or adding something to this equation. Or we may say, why don't I take this equation and then subtract the second equation. Therefore, we need to kind of fix this strategy quite clearly. So what we're going to say is, if I'm going to transform equation number 2, how we are going to talk about it is, we are going to say subtract from equation 2, right? This is kind of a, we are not saying that other techniques are wrong, but in an algorithmic approach, it is easy to standardize the technique, and it will be wise to standardize the technique. Then we can look at an computing or a program that can actually calculate this. Okay, so when we want to change equation 2, we are going to say, please subtract from that equation a multiple of another equation, right? So here we have only one more equation, which is equation number 1. So let's talk about subtract from equation 2. What we have to subtract equation 1. Okay, but if I simply subtract 3x minus 4x, we are not going to eliminate the x here, so we need to multiply this equation by something, right? And what am I going to multiply it with, right? I'm going to multiply that equation by 3 by 4 times 1, right? So how did we get this 3 by 4? We get this because the 4 is the coefficient of the first equation, right? And this forms a very, very, very important number, and in fact this is called the pivot element, right? So why is this important? Because this is the number with which actually we are dividing this equation. Now what we multiply is not a big issue, but then what we divide can actually create small issues. For example, what if the pivot element has 0 there? In fact, when there is a 0, we are not even going to call it a pivot, because it is no more a pivot element, right? You can't divide by 0, right? So that's why it carries certain importance, and therefore we call it the pivot element. So what we are going to do is, we are going to divide this first equation by 4 and multiply it with this multiplier, which is 3, right? So that's how we are coming up saying the 3/4 of 1. So let me write down here what is 3/4 into first equation. That gives me, this is going to be an x, so that is this is going to be a 2, therefore this will be a 6y equal to the 4 and 4 cancel out, and we'll get a 3 here. Okay, so this is my 3/4 of the first equation. Let me write down the second equation on top here. There will be a, so there's a mistake here, so this should be a 3x here. So this will be now 3x plus 2y equal to 11, and we said we want to subtract here, so we subtract this out, so these two get cancelled. So this is going to become 8y, 11 minus 3 is equal to 8, and therefore y is equal to 1, right? So okay, so this is the calculation we are doing. We can substitute this back in any of the equations and find x. So let us finish it off. So this will be a 2, 11 minus 2 is a 9, so 3x equal to 9 means that x is equal to 3, right? Therefore, more than trying to solve for it, what we're interested in is what is actually happening in elimination. So let me just write down the other the equations that elimination is bringing up, right? So the first set of equations we had is 4x minus 8y equal to 4 and 3x plus 2y equal to 11, right? Now we do a pivot operation, or if you want, we can even call it now a row operation, right? We understand now when we call it a row operation. Why is this a row operation? Because remember that the coefficients can be put in a matrix where we can also look at them as a single row. Anyway, we'll be talking about that later. So we call this a row operation, let's say. After this row operation, what was the row operation we did? We picked up row 2 minus 3/4 of row 1, or we can say second equation minus 3/4 of the first equation, and therefore the first equation didn't change. Remember that this change was for equation 2, so I can write it here that basically we are looking at second equation getting changed. So this gave us 4x minus 8y equal to 4, and the second equation is here, which is 8y equal to 8, right? There is something interesting that's happening here. let's try and look at it in the matrix form. So let's look at this equation and let me try and write this down in a matrix form. So we'll get here a 4, a minus 8, 3 and 2, right? This would have been our coefficient matrix. Let's try and look at the coefficient matrix here. It is 4 and minus 8, 0 and an 8, right? So remember, I didn't include the right hand side, so let's not worry about the right hand sides at this point. But when we see this transformation, what it's effectively attempting to do is, it is making, elimination is trying to make an upper triangular matrix, right? So this is what it's attempting. It's picking up a matrix, coefficient matrix, and trying to make it an upper triangular matrix. And what is the way it is doing? We can call it as row operations, right? Apart from noticing that it is upper triangular, let's also try and note one more important fact. In order to calculate the y value from the second equation here, the modified second equation, we had to divide it by 8, right? So again, if we look at this value, plays an important role because this is the number with which we are dividing it in order to calculate this, right? So just try and imagine if this coefficient was not there, right? So if this coefficient was 0 or whatever, we may land into trouble because we can't really calculate the y value here. So these are the terms that play a crucial role, and that's why they are called as pivots. So let me introduce the concept of pivots by first transforming this to a matrix, and then we will talk about what are actually pivots. Of course, we have an idea now. So there is another interesting fact that we can notice here. You see that okay, we understood in the first equation that 4 was the pivot, and interesting fact is the pivots are coming up in the diagonal after the row operations in the upper triangular matrix. That's one more fact to notice, that the pivots are appearing on the main diagonal in the upper triangular matrix. Okay, so what we will do now is we will try and represent this as a matrix, and we will see, try to relate concepts that we have learnt earlier to the matrix form, right? So we pick up this set of equations, 4x minus 8y equal to 4 and 3x plus 2y equal to 11, and we can represent this as the matrix, right? So now let's try and write the equations using the matrix form. So I can put it as 4 and minus 8, 3 and minus 2, okay, 3 and minus 2. Now if I write it here as x and y and then put here as the right hand side, this is my matrix representation. Now what is important to note here is that we are doing what is called as a matrix vector multiply, right, which is something that probably we did not define but is going to get defined now from these equations, right? So linear equations can be written as coefficient matrix times the variable as the vector and the right hand side as a vector form, right? And how do we define matrix vector multiplication? Now there are two ways to define it, so let me talk about both of them. So here is one way, right? So we can talk about 4 and minus 8. I am writing it in a row fashion because it will be easy to visualize this, but actually this is a vector, right? So understand that this is simply the row vector. We should write it probably in the vertical fashion, but since this is present as a row, it's easier for us to understand, so I'm writing it like this. And there is something interesting here. xy again is a vector, we can clearly see it's a vector. I'm putting a dot here, right, and we know what it stands for. It's the dot product, right? So let's see what happens when we look at this. So what's the dot product of two vectors, two column vectors here? We know that this is going to become, so we just put a line here and try and write this here. So this is going to be 4x minus 8y, and for the second one it's going to be 3x minus 2y, right? So this is the kind of row picture that we had studied, right? What we had done was we had taken the equations and we had plotted lines for them, and we had tried to understand what's actually happening when we try to solve linear equations. And we figure out now that basically it could be called the row picture because we are essentially doing dot product of a row vector times the column or the variables here, right, which means that it's the dot product of the row and therefore it can be now called as the row picture. Okay, now how can we talk about the column picture here? What should be the column picture, right? This is what we had written down quite earlier in the last session also. So now let me write this down as 4 and 3 as the column times x, the first component, plus minus 8 minus 2 times y is equal to 4 and 11. Now what does this convey? This talks about what linear combination, right? We are talking about the linear combination operation here, and the question asked for solving this is nothing but what are the constants or what are the scalars that x and y must take so that the linear combination of the vectors 4, 3 and minus 8, minus 2 lead me to 4, 11, right? Since the meaning of the equation changes here, we are looking at the column view here, we call this as the column picture, right? And what's the definition of a matrix vector multiply? So here is the definition of a matrix vector multiply. Either we pick up each row and take the dot product of the vector like this and come up with this answer, so that's the matrix vector multiply, or pick up each column and do a scalar multiply of the column with each of the corresponding components in the vector, in the column vector here, right? So that's how we pick up the first column, the first component, second column, the second component, and take the linear combination of them to provide the right hand side. So this linear combination is the equation form that we are looking at. Both are equivalent. Only thing is we are changing the view and trying to understand what's the row picture and what's the column picture. Okay. So what we should ideally be doing now is to understand what is elimination doing with respect to the row picture and column picture. How are this, what does it mean to solve these equations, and what do these pictures convey to us, right? What's the insight that elimination is giving us? That's what we should ideally be talking about. But first what we will do is we will get this algorithm perfected well for us, and then we will talk about the insight that these pictures can convey regarding elimination. So what we will do next is we will pick up we'll move to R3 and talk about 3 equations, say with 3 variables, and let's see how to use elimination there, and the concept of pivots etc. will become much more clear for us there. So here we move to R3. Here we have 3 equations in 3 variables. Okay, now what should be our idea as per elimination, right? So what we are going to do now is, from the second equation we want to eliminate the x component, and after that proceed with the remaining, right? So let's first attempt this. How do I eliminate the x component here? I can eliminate this if I am able to subtract this, okay? But then if I have to subtract this simply doesn't get eliminated. I may have to probably multiply this by 2, but that is just human comprehension. Remember what we did earlier, we talk about what is called as the pivot here, and we are going to use this coefficient of the second equation. This is the one we are going to talk about eliminating in the second equation. So I use the pivot, and therefore my multiplier, right, the multiplier is becoming this coefficient, which is 4 divided by this pivot, which is equal to 2, and therefore my multiplier becomes 2. So I have to multiply this entire equation by 2, and I'm going to subtract it from the second equation. So what's the transformation we are writing? We are saying second equation minus 2 times the first equation. And where should that go? That is the transformation that happens in the second equation, right? So instead of doing it with equations, now that we have an idea of how do we put it in matrix, so why don't we write the coefficient matrix of this and try to proceed from there on, right? So let me pick up the coefficients, the 2, 4, minus 2, 4, 9, minus 3, minus 2, minus 3, and 7. So remember that we are trying to work with the second equation, and how do we get the multiply for the first? So now I think I can start talking about row. Since we are working on rows, we can now call them row operations. What we are going to do here is, let me write this down. We are going to say row 2 is going to be set to row 2 minus twice row 1, right? So this is how we describe the operation. And now see that it is much more clear when we describe this in terms of row operations. So let me move to the next page and then continue from there. Okay, so when we perform this operation, there is no change to row 1, so this remains as it is. Obviously there is no change to row 3 as well, so that remains as it is. There is a change to row 2, so let's calculate that. 4 minus twice of 2, that's a 0. 9 minus 8, that's going to be a 1. Minus 3 minus 4, that is a minus 3 plus 4, and that's going to be a 1, right? So this is my transformed matrix after my first step of elimination. Okay, remember that elimination is taking us towards forming an upper triangular matrix. Now in an upper triangular matrix, we want all the elements under the main diagonal to go to 0. So the next one that we can look at making 0 is this guy, right? So why don't we eliminate the x component of the third equation, which means essentially we have to talk about a row operation on row 3, right? And what should that be? Row 3 must become row 3 minus, right? So look at the way that we are writing. We update the row. How do we update? From the original values of the row, we subtract a multiplier times another row, right? Okay, now we could use either row 2 here or we could use row 1 here, right? Suppose you try to use row 2, it's of no use because we have already eliminated the coefficient of x in row 2. There's no point in using row 2 here. So we are forced to use only row 1, right? Okay, so let's look at, so there has to be a row 1 here. Only thing we have to understand is what's my multiplier to row 1. And again, how do we calculate? We pick up the pivot element. Pivot element here is 2, and that is the number with which I'm going to divide this. The multiplier, the multiplier is going to be this coefficient divided by this 2, where I can write here it as minus 2 divided by 2, that's a minus 1. Therefore, this is what we need to do, right? So let's do this calculation next. So there is no change to row 1, 2, 4 and a minus 2. No change to row 2. In this case, there is a change in row 3. Minus 2 times minus 1 times this. I think this is going to be simple to just add these two. So this is going to be 0. This is going to be a 1 here and a 5. Brilliant. Now that we have made all the values in the first column except for the pivot to become zeros, now let's move ahead and look at this 2 by 2 matrix and apply elimination recursively in the 2 by 2, right? Okay, look at this and ask, this is the main diagonal, so which is the element that must go to 0? So this is the one that must go to 0. So what is the operation that we would like to perform now? We want this to change, therefore we have in effect that row 3 must change, and in our algorithm we are going to say it is always row 3 minus something. Okay, now we could choose, right? So if we want to make this 0, we could choose either from here or from this point. Okay, either we could use row 1 or we could use row 2. Okay, suppose we use row 1 and we try to eliminate this element, right? Possibly this may go to a 0, but in effect what would happen is that since this is a 0, whatever operation we perform here, there will be some non-zero element which may stick on at this point, which means we will have to go back again and rewind because we eliminated this, and now we are, because of our operation now with row 1, we are getting back an element here. So that probably is a stupid move, so let's not do that. And remember that we are trying to work only with the 2 by 2, which is we are saying recursively work with this. Let's not go to row 1 because our view is only this these two rows, okay, and these two columns. Now if I have to work on this, my pivot is a 1 here, so I have to divide by 1, and for getting the multiplier it is going to be this coefficient divided by the pivot, which is 1 by 1, which is 1, and therefore this is simply going to be R3 minus R2, right? So let us do this calculation next. So let me write down this. No change to row 1, no change to row 2, there is a change to row 3, so let me update 0 minus 0 is going to be a 0, 1 minus 1, that's a 0, 5 minus 1, that's a 4, and this is what we get. Now look at this important fact here. this matrix is upper triangular and the first pivot is 2, right? We are also going to get other pivots. Look at this. This is my second pivot element. That's my third pivot element. The moment I have 3 pivots here, we need the 3 pivots in order to calculate the 3 variables values. Okay. And also we can see the definition of a pivot from here, right? In the first row, this is the first non-zero element. In the second row, this is the first non-zero element. In the third row, this is the first non-zero element. So what does a pivot mean? That's the definition we're bringing up. We're saying the first non-zero element in a row, right? It's a very important definition, and the definition of the pivot itself includes the non-zero term, which means that if we find all zeros in a row, that row does not have a pivot. No, we can't say that the third element, the position there is supposed to be a pivot and has happened to become a 0. No, we don't call 0 elements to be pivots at all, because the definition of a pivot says that it's the first non-zero element in a row. Okay, this is only one aspect. We have got the matrix as upper triangular, but how do we actually solve the equation? We still didn't solve the equation, right? Which means that we have to also look at the right hand side, right? So let me look at the right hand side here. The right hand side is a 2, 8, 10. Okay, we have a right hand side column vector which is 2, 8, 10. Remember that we have to solve the equation. This is quite easy for us to use and solve, but the problem is this has got transformed, right? This is a transformed matrix from our original matrix after row operations, which means that effectively we must be doing the same row operations on the right hand side as well, right? So we have done it only with the coefficient matrix. So let's use this row operations and perform them as well on the right hand side column vector, right? So let me write the operations down. First is R2 minus 2R1. So we write this here saying R2 goes to R2 minus twice R1. So let's calculate that. So there is a change only here. So let me write down the first and third without any problem. 8 minus twice this, that's going to be a 4, right? So what's the next operation that we perform? Next one is again is on R3. R3 goes to R3 minus 1 times R1, or R3 plus R1. So but I have to write it in that fashion so that we be consistent, just to be consistent. So R3 minus 1 times R1, right? So what will that give us? Effectively just have to add them. So the 2 and 4 will remain here. This would now become 10 plus 2, which will become 12. Okay, and after that we had one more operation here on R3, which is R3 minus R2, right? So from this point we said R3 is assigned to R3 minus R2, therefore this would say that 2 and 4 remain same. 12 minus 4 is an 8, and that will be the final, because we had 3 row operations. Look at this, we had 3 row operations. We performed them on the column vector, which is 2, 8, 10, and it's got transformed to 2, 4, 8, right? So let me put this matrix down here. The 2, 4 minus 2, 0, 1 and 1, and 0, 0, 4. Now we have an upper triangular matrix. So we can write this in matrix notation. X, Y, Z is going to be the right hand side, 2, 4, 8, right? Now look at these elements. We'll get to know why these are now pivot elements. 4z, right? So we calculate the answer from the last equation. 4z is going to be 8. 4z is going to be 8, and therefore all that we need is pick up the last element and divide by the last pivot or the nth pivot, and we get the last variable's value, right? We don't have to even write the equation to get it. So simply looking at this, we can say z is going to be 8 by 4. last coefficient of the last component of the column vector on the right hand side divided by the pivot, last pivot 8 by 4, that is 2, right? Now we have to substitute for this in the previous equation. So how do we do that is, finally this is the one that's going to help us divide this. Therefore we have y plus z giving us, this equation says y plus z giving us 4. Now use this value here and this we substitute it here, right? That's why this is called as back substitution. Remember, elimination happened in the forward direction. We had a matrix and we landed up here. Elimination is moving in the forward direction, whereas substitution is happening in the backward direction. That's why this sometimes is called as back substitution, right? So we substitute for z equal to 2 here and therefore we get y is also 2, right? Now remember, if this was a 2 here, we would have divided this value, after the subtraction divided by 2. That's why that's the pivot element. Okay, the last equation is 2x plus 4y minus 2z is 2. So substitute here, this is a 4, that's a 8 minus 4 is a 4, 2x equal to 2 minus 4, so x is equal to minus 1, right? So that is the solution that we get. But remember, we use 2 steps here: elimination in the forward direction and substitution in the backward direction. Key points to remember: in elimination we had a original matrix from where we reduced it to upper triangular, and the pivots have got exposed on the main diagonal of the upper triangular matrix. So let us just fix this strategy if we have n equations and n variables. So let's say that I have a square matrix here, n by n, which means that I have got n different variables, n different equations, right? And we are only working on a square matrix as of now. We may change it much later. Okay, now what should be the strategy of elimination? First thing is, we don't bother the first row at all. Okay, that has remained a constant that we would have seen in the last 2 examples as well. What is the first element that we must attempt to make it go to 0? Here is this guy, right? So the first thing is going to be A21 must get eliminated. Okay, followed by what? Followed by A31, that also should get eliminated, and so on till AN1, right? So that's the first strategy. We must try and do that many operations that we are able to eliminate A21 till AN1, right? That may take that many row operations, and let's try and understand how many row operations would have occurred here. We would have probably used n minus 1 row operations. And what is the pivot that we are using for all these row operations? Using A11 as the pivot element. Very good. Now that we have eliminated this entire column except for A11, we just have to look at the resulting, right? Remember it need not be just A22 here. There would have got values would have got changed here because of these row operations. But effectively we are now going to look at an n-1, n-1 matrix, a sub matrix, right? And what should be the next level of strategy? We should probably try to eliminate A32, right? Just an element under this, and all these must now disappear, right? So A32, A42 and so on till AN2. And how did we do it? Okay, how many row operations do we do now? The matrix itself is now only n-1, n-1, and of that one is remaining, all the remaining, one we leave as it is, all the rest under the first column we are going to eliminate. So that makes it n-2 row operations, and we did it using A22, right? So remember, it's need not be A22, it could just be A-22 also, because that could change, but that was our help to keep it as the pivot and work. I hope that you get this idea. So we keep going like this, and till where do we go, right? We go to the last maybe a 2 by 2 matrix, and we are actually looking at the last strategy here. And what should be the element that must go to 0? That must be the nth rows, n minus 1 column value, right? So the last one will simply be a nth row and n minus 1, right? That is the guy we must eliminate, and that just needs one row operation. It just needs one row operation. And what did we use, right? Using what as the pivot, right? I can just put maybe some a dash or a double dash, a triple dash, I don't know what it is, but we use the previous row and the same column as pivot, right? So work this out and see if you're not able to get it. It's simple. In the nth row, n minus 1 column, this is the one we're trying to eliminate. How do we eliminate that? Using the one above, so that must be the n minus 1 row, and obviously it's still in the same column, so it's n minus 1. Okay, and that's the strategy of elimination. And strategy is that elimination moves forward, and ultimately this is not enough. We have to perform this as well as on the right hand side, the column vector. All these operations need to be performed on the right hand side column vector as well, and we can understand how many row operations are going to take place and what are the elements that they're going to look at as the pivot, right? Just for the sake of just an addition, we can easily add this and see. So this is the idea. So we have n minus 1 initially row operations, followed by n minus 2 row operation, and so on till 1. What would that be, right? This is going to be n minus 1 into n by 2, or we can say, in fact, I am having order of n square row operations. We are having order of n square row operations. Now each row operation itself may have several floating point operations. For example, it may talk about, if you look at a row operation, we may see that we may need a multiplication on this entire row, and after there is a subtraction, right? Which means the very first row operation we would have done n such computes, because we have n such subtracts, n such multiplies, etc. Right? So in effect, what would happen? Though this reduces later, right? So if when we start looking at this, you will find that actually it's going to be n minus 1 here. Further, it's going to be n minus 2. But in effect, when we try to add all this and look at the big O notation, the total number of floating point operations is going to become order of n cube, right? There's nothing less than this that you can actually do this elimination, and at the end of this you will find that we get an upper diagonal matrix on which we perform back substitution and get our answer. Okay, so I'm hoping that the process or the algorithmic approach of elimination is clear. The strategy of elimination must be clear. But there are cases where this may fail, and that probably is going to be the topic for our next session. So let us end this session with a prayer. Om Shanti Shanti Shanti.